So, good afternoon, everyone. Thanks for joining me in this presentation. My name is Andrei. I am a postdoc researcher at INRIA, which is a researcher institute in France attached to the University of Lille. I'm presenting today the work entitled Accessing Power Used Effectiveness in Serverless Computing, done in collaboration with my colleagues Nathan Leblond, Kélian Lévesque, and Romain Rouvois. And so I'm going to start with some definitions about what is the power used effectiveness, more specifically. But first, to give some context, our project and our team, we are very interested and focused on the energy impacts of computer science. In the last few years, it has gained more visibility and it's a very hot topic. As the numbers are getting critical, we are very interested on this topic. So some statistics, for example, as we have shown here, the energy consumed by data centers themselves already achieved 1% of global energy consumed, and they may continue to increase. So we need to act towards improvements of these measurements. Serverless computing, we believe that has the capability and the potential to reduce energy consumption on cloud platforms by the characteristics of reusing different scenarios, environments, and by releasing the resources when they are not needed anymore. And so we are combining these contexts in this work, and mainly because we observed that in the context of serverless computing, all the measurements, the majority of the measurements that we found in the state of the art rely on estimations of energy consumption. So we need to move towards more accurate measurements as well. And so we try to address some of these points in this paper. The main contribution here is then a preliminary exploration of the power used effectiveness of serverless computing. I'm going to define power used effectiveness in the next slide, but here to enlist our contributions in that direction, then we quantify the energy overheads of serverless functions and executions. We propose a completely reproducible scenario for these experiments. We demonstrate how Power API, which is the tool that we use it to measure our energy, the energy consumption of our platform that provides fine-grained energy measurements. We adapted a suite of benchmarks called function bench to be executed with Knative. And we propose a first approach showing how to compute what are named the VPU and the CPU, which is the virtual power used effectiveness and the combined power used effectiveness. And in terms of serverless computing, we do all these explorations, looking at the different starting mode of the functions, varying the size of the serverless platforms, and also looking at different loading of serverless functions. It starts then with some definitions. So the power used effectiveness can be defined as the ratio between the energy consumption by the data center level over the hosted IT equipment. So here in this paper, we are not interested necessarily on reducing energy consumption. The idea is if we need to consume this amount of energy, we want to be sure that this is well used. So this is what the power used effectiveness measures. So is how much energy you are really making a good use based on what you are, let's say, wasting. So as a ratio, this metric, the optimal value for this metric is considered to 1. And more specifically, we are interested in the variations called virtual power used effectiveness and the combined power used effectiveness. These extensions here, they want to capture, the goal is to capture the software layers of the power used effectiveness, because as I defined it in the first bullet point here, the power used effectiveness metric was first created for for the infrastructure, for the physical part, and not for the software layers. So then we have these two other metrics that want to capture it. Since we are in a serverless workshop, I'm going to skip the definitions of serverless computing, and I'm going to directly for our methodology. So here is our infrastructure, and with the QR code, you can find our repository with all the artifacts, and everything is totally reproducible. So what we did was the following. Looking here, we have our cluster node that we deployed Kubernetes on top. On top of Kubernetes, we deployed Power API, which is the tool that will measure the energy consumption, and we deployed Mini.io for our buckets and data object stores. On top of Kubernetes, we deployed Knative as our open source platform, where we have two main namespaces. The Knative serving, which is the set of services that manages all the serverless behavior as the autoscaler and etc. And our Knative function namespace, where the functions are executed directly. So what we do to measure the metrics that we want, we focus in different levels here for a set of experiments. So going step by step, I'm going to highlight here on top of this schema, the equations that we compute. So first, we start defining what is function performance for us. The function performance is the time that a function was executed inside the pod over the execution of the pod itself. So then we can capture the difference of the exactly execution of the function. So with that, we disconsider the deployment of the container or the removal of the container, the pod, I'm sorry. So with the function performance, we advance with our formulas. So the first thing we compute is the virtual power used effectiveness, F, meaning the function level. So at the function level, we compute this metric by considering the total energy consumed by the pod over that energy consumed by the pod times the function performance. That ratio tells us how well the energy of the function, sorry, let me restart. It tells us based on the energy consumed by the pod, how much of a good use we made for the function execution properly. And in the diagram here, it means that we are looking only at this level. So using the pod, considering the pod and the Knative functions environment. Moving a bit further, if we want to look to the entire Knative namespace, now we consider as the ratio the sum of all the energy of the Knative namespace plus Mini.io, that it's outside Knative, but we prefer to include Mini.io here since it is in use of our platform. The energy of the pod over the sum over the energy of the pod. So then here we have the ratio of the energy consumed by our namespace, our Knative namespace, over the energy of the function. And in a global level, we have the same metric in terms of the Knative, the Kubernetes platform. So here we consider the sum of the entire node, the energy of the entire node, subtracting the cost of Power API, because in an ideal scenario, we would have the tool measuring the energy from outside over the total energy of the pod. So here then we have the ratio of the consumption of the pod over the entire platform. So then until here, what we have is the virtual power used effectiveness. And the question now is, knowing this metric for the function level and for the Knative level, how can I combine both to know more exactly the consumption of my serverless platform. Then we come with the combined power used effectiveness in terms of the Knative namespace, where we multiply the function level and the Knative level. So then we have this combined metric. And for the combined metric of Kubernetes, then we multiply the combined metric of Knative, considering now the virtual power user effectiveness of Kubernetes. So with this final metric here, we have a global view of the energy consumed by Kubernetes, considering the entire infrastructure. Here is the complete list of the equations. And as our design of experiments, we designed two batches of experiments. The first one was focused on profiling these metrics for individual functions in different combinations of input sizes. For that, we looked at the different modes of executions on serverless, cold, warm, and hot, but we fixed the auto-scaling mechanism, and we fixed also the platform. So we had only one control planer and one worker, so we could profile individually each function with each different input size. And in the second batch, we are interested on auto-scaling impact. So then we varied the worker nodes in 1, 2, or 3. And we also increased the concurrency target from 50 to 70 to 100%. As I mentioned, we adapted this suite of benchmarks called Function Bench to run with Knative. In this paper, we used only these 5 functions, but we adapted more, and they are all available as well in the reference. You can find it. But for here, we had a total of 10 combinations of functions and inputs. And for this presentation, because of the time, I'm going to present only the results for the first batch. And here is a very preliminary look at the general results that we have. So in the x-axis, what we have is the combination of functions and the input size. And in the y-axis, from the top to the bottom, what we have is the mean execution time, the mean CPU usage, mean memory usage, and the mean power usage. By here, we are not computing yet the metrics that we are interested, which are the power user effectiveness. This is just a preliminary profiling to take a look on the pattern of each function. So one thing that it's very clear in the figure, for example, is that Limpac and matrix multiplication are very memory bound due to the allocation of the matrix that they need to do for the executions, while modeling training and video processing, they are not that much memory bound. The values here are not 0, but because of the scale, it seems so. But they are more CPU bound than memory bound. And in terms of mean power usage, as Limpac and matrix multiplication use a lot of memory and CPU at the same time, they consumed more power, while video processing and modeling training not. But we are more interested in the following results. Here, what we have is the virtual power used effectiveness for the 3 levels that I defined earlier. So from the top to the bottom, what we have is at the Kubernetes level, the Knative level, and the functions level. They do not have the same scale because we are not really comparing them, but we are going to do a progress analysis from the bottom to the top to understand our goal. What we have with the different colors are the function modes, so cold, warm, and hot. And again, in the x-axis, we have the functions and the different inputs. What we can see first, looking to the execution mode, is that the purple functions, the hot instances, they are pretty close to optimal values in terms of the power user effectiveness, which means that if we expend some amount of power deploying the platform, the hot instance functions make almost 100% of good use of this energy. There is no extra energy wasted on preparing, deploying the environment, and so on. What can be seen on the contrary for the cold and warm functions that increase in comparison with the hot functions. But here again, since we are not trying to reduce energy consumption, but to optimize the usage of the energy consumed, what we have for each pair of functions is that as far as we increase the input size, we decrease the power used effectiveness. Why? Because if we increase the input size, it means that this function was executed for longer. And if it was executed for longer, it makes a better use of the all energy used to deploy the environment. So that's why cold and warm functions here are not good for this metric, because and small functions, sorry, let me rephrase. Fast executed functions are not that good for this metric, because it means that if we spend X amount of energy deploying the platform and we only use it for a few seconds, it's a waste of energy. So that's what this metric captures. And now, as I mentioned, understanding from the bottom to the top, why, for example, for video processing, the PUA here was optimal, close to optimal, and here it's not that much. It starts to be invisible. The point is, from the function namespace and to the Knative namespace, here we add mini.io, which was not included. So at the function level, the metric did not capture the use of mini.io, but for the Knative level, mini.io was included. So then we could capture the influence of one more software layer on our platform. And that's why, for example, that here, again, the scales are not the same, but for example, for Limpack and matrix multiplication, there was no increasing in the values, because we didn't use mini.io at all for these functions. But the contrary is not true for the video processing. And finally, the Kubernetes namespace is the one that arrives at the biggest values, because then we have more services, more pod runnings for Kubernetes. And because we have these gaps when only looking to one metric or another, we are more interested in the combined power used effectiveness. So from the top to the bottom, the Kubernetes namespace and the Knative namespace. Here we have the combinations of the different plots that we saw in the previous figure. So here, the results on the bottom reflect the combination of these two metrics here. So if we multiply the results from here to here, is what we have in the combined power used effectiveness. So this metric captures a more global view of the metrics. And again, in terms of the Kubernetes, now we see the real impact of all the services deployed on Kubernetes in terms of the power used effectiveness. So just to rephrase the meaning of the power used effectiveness, as I mentioned, the optimal value is 1. If we have more, it means that for each watt that is injected in the system, the remaining value of the total value is how much more we wasted to execute what we need. So let's say if we expend 2 watts to execute a function, it means that from each watt that was input in the system, in the infrastructure, we spend 1 more watt to execute the function. So that's why we want to be as much as close to 1, to not spending more than we already spent. And finally, if we ignore now the types of functions that we have, and if we translate all the results in execution time, here we have the linear regression of the combined power used effectiveness over the function's execution time. What we can see again with the colors is that for the hot instance, doesn't matter if it's a fast execution function or if it's a longer function, the power used effectiveness is always close to optimal, but it was expected. But what is very interesting here is that for the cold and warm functions, for very fast executions, they do not have a good performance in this metric. But if we let the functions live for longer enough, they can achieve optimal power used effectiveness. Meaning that in serverless specifically, fast executed functions are not the optimal use case if we are interested in these kinds of metrics. So all functions at once, they are going to be cold or warm, but the idea is that if we let the functions stay in the platform for longer, they will pay the price of energy consumed. So to conclude, our finds acknowledge that first, the starting mode of functions in serverless platform is crucial, as I think all other areas in serverless computing. But here we show that hot startups are really beneficial in terms of the power used effectiveness. And even as serverless was designed for very fast execution, functions from milliseconds to seconds are not ideal. And I think that was very interesting to have the keynote in the morning when we were discussing also about the not necessarily having fast execute functions for serverless anymore. Meaning that maybe this is not the only thing that defines serverless computing anymore. We have many other aspects. So this is a hint that maybe that is true. It would be better to have more longer executions, especially for the energy consumption part. And because in fact, if we have very fast functions, we showed that they can have an increase of by 2.5 power used effectiveness at the level of the functions, and arriving by 7 times worse performance in the global view with the combined power used effectiveness. We intend to expand our experimental setup, including a bigger range of functions and also including workflows. We want to add more metrics about the power used effectiveness, such as the partial power used effectiveness that is intended to model better external but included services such as Mini.io, because in our case, we kind of included Mini.io in one of our namespaces, but this partial power used effectiveness would capture it better. And mentioning the inclusion of workflows on serverless computing, if you're also interested, I'm presenting with another colleague tomorrow a tutorial about how to use serverless computing with scientific workflows. That will be connected soon in these perspectives here. We thanks for the projects that support our research. And here are the references for the slides. And I conclude my talk. Thank you very much for your attention. And I'm open to questions or any other discussion. Thank you.
Thank you. Do we have questions from the audience?
Yes.
So you say that like if you have a function that takes a very short time to be executed, then serverless is not really the ideal, right? In that situation, what would you say is a better solution?
Yeah, the thing is, if you don't have other option than just execute that function for just once, I think we don't really have a better solution for now. But if you intend to re-execute that function later, the option is to not kill the function, to wait the next time to redeploy the function. Right. The point here is not, I'm not saying don't use fast executed functions. I'm saying if you are going to use this kind of functions, at least keep their environment alive in the platform for when they arrive, they are not cold or warm anymore.
Can I ask for an enterprise setting, let's say for a web server, that executes task, but you have to wait, it may have to wait like for some minutes or seconds in order for the next request to arrive. Would you suggest keeping the container alive, or would you suggest like for the idle time killing the container and reinitialize it after some time?
Yeah, that's the tricky part. I mean, it's always a multi-objective optimization, right? It always depends on the combination of the make span, so end-to-end execution time, the cost to keep the process alive, the energy consumption. So I think it really depends on the use case, on what is your goal. What we show with this paper is that if your primary goal is the energy consumption, then the best would be to keep the functions alive. But again, it's a multi-objective problem, so I would need some Pareto curves here to show some optimization.
Okay.
Yes.
You go back to slide 12. Yeah, I have a hard time understanding for the first workload, right? So it has a lower execution time, a lower CPU usage, and a lower memory usage. Why the power usage is similar to the second one? What drives up the power usage? If it's running shorter, the resource utilization is smaller, but it kind of has a similar power usage. Why is that?
Yes, so here there are some challenge on the experimental side. So first thing, as you can see, the bars that sometimes are kind of large. We do not run so many repetitions for this step of our project. So as you can see here, I wouldn't say, for example, that these two bars are very different considering the standard deviation of them, for example. So the first thing is that we don't have a lot of executions to statistically validate that behavior. But again, here, as we are talking about the power usage, it's for the entire node. We don't have the isolations that I showed in the other figures. So maybe here we have everything else that's running on the platform that could affect this behavior here too. Okay. Yeah.
I think by your talk, I have two questions. The first one is the runtime is influencing the execution, right? And then if I run Python, or if I run C code, I will not have the same results, right? So which runtime will you use?
Yes, I agree with that. Here we are using all Python. They are all Python functions, but it's one of the things that we discuss also, that to experiment with different runtimes to do a larger analysis.
And can you go back to equations? Can you explain us the rationale for this equation as well? Instead of so it's 8. Yes, you have energy
Here.
Total energy divided by the total energy multiplied by function. What's the ratio of this?
Yeah, so here
It could be 1 over function performance.
yeah, here as we consider the function performance, the ratio then is here we consider the entire pod, and we are doing the ratio with the execution of the function. So this is how we capture the execution of the function inside that pod.
But you can simplify it. It's 1 over function performance.
Simplify how? Sorry.
Remove energy. It's 1 over function performance.
Okay, I see what you mean. Yeah. Yeah, okay, the equation was not really clear at that point. Yeah, it's not one over the function performance itself. Yeah, no, I see your point.
And so this is the ratio of pod execution over function execution.
Yes.
In some sense, but
Yeah.
energy pod is.
Yeah. No, I agree. I need to. Yeah, I will double check with the paper if I put the correct equation here, but I agree with your point. But the meaning is that it's the ratio between the execution of the pod over the execution of the function.
One last is you can actually, once you have combined, look at like the code itself and kind of do some approximation of the time it would take to execute like those instructions instead of running the thing. So I have some code, I look at the instructions, and so okay, it's going to take, I don't know, 100,000 instructions. But okay, maybe it's not possible because you have external tools, but
yeah,
so you need to empirically measure the time, but you put this kind of offline while looking at the instructions themselves. Is it something that is done? Like evaluating the energy cost of something?
Just the analysis of the code.
Just the
yeah. I agree that it's very interesting. I don't remember seeing something doing that directly. But one thing here is that the serverless behavior is very unpredictable. So let's say if the pod runs out of memory or if there is an auto-scaling requirement and the behaviors can really change. So a pod can be killed and redeployed and all of that, it's difficult to capture. So in that sense, I think in a preliminary study, it makes more sense to execute the functions and the pods themselves to do some profiling with some more repetitions to get statistical values. But I agree that that can be an interesting technique as well. Thank you. I think we are done with the questions in the audience.
Are there any remote questions? I do not see anything in Discord or Zoom, so I think we can move to the next session.
Yeah. Okay. Oh, thank you again.
Thank you for your talk. Okay, I can see your screen. Sharing works very well.
Okay. So I'm going to start.
Yes, go ahead. Thank you.
Okay. Hello, everyone. I'm Xinghan Chen from the University of Washington, Tacoma. Today, I will be presenting our paper, Large Language Model for Serverless Function Generation, an investigation for FaaS performance. The work addressed the interest of two rapid evolution files, generative AI and serverless computing. Here is the outline for today. We will start with the motivation behind using LLM in FaaS, define our research question regarding quality and performance, detail our litigious methodology, specific how we controlled our cloud variability, and finally discuss our result and the future of agentic AI in the space. So I assume most of you are familiar with serverless computing. Serverless platform like AWS Lambda offer massive benefit, rapid elasticity scaling, scale to zero capability, and fine-grained building. We are witness a paradigm shift in software development. The software development workflow is now more commonly evolving into prompt, generate, and deploy. For serverless computing, developers are increasingly using LLMs to generate function code, infrastructure template, and configuration scripts. The promise here is speed, accelerating deployment cycles and lowering the barrier to entry for building complex cloud applications. Serverless deployment with LLM appear quite promising. You prompt an LLM, you get the code, and you deploy it. But is it really that simple? This leads us to the critical question: what is the real quality of the LLM-generated code? We aren't just talking about whether the code looks nice in an editor. We need to know about how it behaves in the wild. There is a hidden challenge in our LLM software development pipeline involving three distinct issues. Correctness: does the code actually work? Earlier works focus on functional correctness, but that is just the baseline. Performance: is the code efficient, or is it silently slow? This is a crucial question because in serverless platform, inefficient lead direct to high latency. And third cost: is it burning through the cloud budget? Since serverless billing is based on execution, duration, and memory, performance issue directly translate into financial loss. To understand the scale of this problem, we first conduct a comprehensive study. To answer those questions, we must divide our models to different categories. We categorize into three buckets: large models, which is larger than 100 billion parameters, like GPT-4, typically cloud-hosted; medium models, which is mostly 10 billion larger, which might run on high-end local cluster; and small models is, for our study, is smaller than 10 billions. It could be run on consumer hardware. This is distinct in vital because we want to know if smaller, cheaper local host models are good enough for serverless deployment. This leads us to two primary research questions. First, research question 1 focuses on quality. When we use smaller versus large models to generate functions for common algorithm or data analysis, how does the code compare in terms of function correctness and maintainability? Second, the research question 2 looks at performance and cost. Once deployed to AWS Lambda, does the code from a smaller LLMs run as fast as the code from a larger LLMs? Does the choice of model impact your monthly cloud bill? Let's look how we test these research questions. Benchmarking function as a serverless is tricky due to noise. We ran our experiment on AWS Lambda in US West 2 with 3 gigs of memory to guarantee full access of 2 virtual CPU core. Currently, we're filtering our result to run only on Intel Xeon Platinum 8259CL CPUs. This removes the hardware heterogeneity often found in AWS Lambda, ensuring that any performance difference we see due to the code, not the cloud providers. We designed 10 distinct tasks resulting in 16 total prompts. This include IO-bound tasks like processing healthcare CSVs and sales analyze data. The CPU-bounded tasks like calculating prime number and page rank. And also we do some CBUS and lead code benchmark tasks. We have tested those tasks on 14 diverse LLMs, ranging from large cloud-hosted models like GPT-4 to smaller local models like QWN 2.5 and DeepSeek. From this slide, we can see the model runtimes and the model sizes. Those models cover from several billion parameters to over 100 over hundreds of billion parameters. And also, we included two different types of inference style for LLMs. The traditional token by token one that direct give you the answer of the your questions, like you prompt it direct tell you what is the result. And the reasoning models, they pretend to think like a real human. So they do one step next to another, and then give you a chain of thought. Then based on the thought, they give you the answers. Here is the token limit. Token limit is a hard limit of how much contents we can feed in and extract from the models in a single transaction. To collect metrics, we use SAF, Serverless Application Analyze Framework. It allowed us to instrument the generated function automatically to profile runtime, CPU user, and kernel time, and memory usage metric for every executions. Now let's discuss what we found it. Starting with the correctness, does the code work? The gap here is strike. So first finding is that correctness is a minefield. Large models in the blue part of the graph is significantly better with an average success rate of 66.7%, and Gemini 2.5 achieve 87.5% of success rate. Small and medium models in the red part is struggle with a success rate of only 29.66. QWN, for example, only success with 12.5 of the time, and even DeepSeek 8 billion. This one is very small and failed on all the tasks. However, correctness depends heavily on the tasks. For well-defined algorithms like prime number generations, models achieve 92.9 success, but on the complex I/O tasking requires specific scheme placing like sales analyze, success rate dropped to 29.6. These struggling LLMs handling algorithm logic better than data processing tasks that require straight adhesive to input formats. We also run static analyze, use Python and Radian. Large models generally produce cleaner, high-quality code, average score of 2.5, and compared to the smaller models, they produce average score of 4.58. These have implications for long-term code maintainability. Moving to the research question 2, what happens when we run the code? First, as a realistic check, only about half of our generated function was functional correct. 16.1 of the function have syntactic error, and 32.1 of function produce incorrect result and were functional incorrectly. This highlights that we cannot blindly trust the LM output yet. And the second is that even the correct code that can be catastrophically slow, the log scale chart showing the runtime difference compared to the human baseline, while large models represented in the blue part generally stay close to the baseline. Some models generated code that was over 100 times slower. This is due to inefficiently loop or improperly library usage. Larger models produce functions with acceptable performance. Result is much more better than the smaller and medium models. For example, at here, large models produce 43 out of 112 chances, which is 33.4%. That is below 100 more than baseline. Otherwise, the medium and small models produce only 22 out of 112 attempts, which is only 19.6 accept rate. A key insight here is the difference between CPU and I/O tasks. CPU-bound tasks like prime number show massive variance. Better models write better algorithm, but for the I/O-bound task like healthcare and sales analyze show smaller difference, approximately only 0.95 times difference. That's why, because the runtime is dominated by reading the CSV file, which makes the efficiency of generated code less important. The total time cost is dominated by the I/O task, not the computer algorithm. And the third finding, the low performance equals to waste money. In serverless computing, time is money. The poor performance translates direct to wasted budget. We found that choose the right model could lead to a 59.6 cost saving for the same task compared to an inefficiently implementation by a smaller model. This cost of inefficient might be the cost of inference might be higher, but the operation cost is lower. If we automatically deploy without check for those costs, organizations could face unexpected and severe billing strike. Let's summary and look at the path forward. To conclude, RQ1, large cloud models are currently superior for serverless generation. They offer higher correctness and better maintainability. Smaller and local models are available for simpler tasks, but are risky for complex workload. They can still be useful, especially for relatively simple or well-understood tasks, but they break down more often on complex or unfamiliar workloads and tend to require more manual debug. To conclude, research question 2, large models generate cheaper to run code for CPU-intensive tasks. For IO-heavy tasks, the model chose matter less for runtime, but correctness remain in the bottleneck. In summary, ARM hold enormous potential, but we must close the gap between generate and the production quality, and agentic closed loop approach is the next step. Thanks for your time, and I'm happy to take your questions.
Thank you.
Any question? Yeah.
I kind of two questions. So the first one is, I'm not sure I understood how you ask the models to generate the serverless functions.
So you need to give them a prompt. A prompt is describing what you want. Like you want to generate the prime numbers. So you tell the you write a prompt that starting with I would like to deploy a serverless function to what platform like AWS Lambda, and this function should take something like n. N is an integer number, and the output is how many prime numbers?
All like text.
Yes.
Because I was thinking about the cases where the functions were not correct.
Mm-hmm.
And I was wondering if you have any thoughts about giving some structure of code as input for the cases where the generated functions fail. Or so let's say for more complex functions that in general they fail.
Mm-hmm.
Have you thought about giving some input saying, I have this standard function, for example, and I want to model it as serverless? Do you have anything?
We currently directly ask the models to generate working functions. We do not give them a working non-serverless application and ask let them translate. This could be a potential work later.
Yeah. Maybe it's a middle step of zero information to some information.
Yes.
Okay, thank you. And thanks for the presentation.
Any other question?
Yes, I have a question. So if I understand correctly, you were using one prompt and then looking on the output. Is that correct?
Yes.
Did you look on like agentic or, those systems where they divide the prompt or, task into smaller tasks and then run and evaluate, actual tests and so on? So it takes longer, but you get pretty much always correct, like at the end, the last task is like verification of tests and maybe deployment and check that, serverless function works and return the results you want.
Yes, we have looked at the agentic AIs, and we are planning to extend to this area.
Okay. Yeah, because that would mean probably that correctness is much higher, but also the time or, the complexity would become much bigger.
What we was not do this at first time is because agentic prompting that require multiple iterations, and it might be harder to control the difference between different models as you prompt it the first time, and the agentic need to return second prompt, and the second prompt will be different for different models.
Right. Yes. Yes. Much more complex. Yes. Potentially.
And question?
Thank you for your time. We still move on to the specificity of serverless in your work today with functions as I said before, how different is it with respect to, I don't want to sell a solution, because in your problems, it's the same. You could have like a regular program, right? Not this one. So does it make this difficult for the
so
you know, to solution? Does it simplify things? What is the service specificity?
So right now the models mostly optimized for generalized computing environment, so for non-serverless. And we want to know that they work better or less likely to work on serverless environment.
But you don't think it's better at solving one?
So currently it's might not as good as the general environment.
Take it that.
Mhm.
In terms of to be exploring or exploiting the trade-offs. Like you have a serverless function that is meant to run over and over and over. So, well, you gave some thoughts on that on your slides. Like for a function that runs multiple times, makes sense to use a more complex LLM model to generate. So maybe there's nothing specific in terms of kind of code that it generates. Maybe it's just for general programming. So perhaps you can say exploit trade-offs like together with the serverless platform. Like if that's a function that's meant to run multiple times, then choose some more complex LLM, which will spend more energy processing to generate that function. Otherwise, use a more simple. So perhaps the thing is backwards. Look at the adaptive generation process. Which LLM to choose to generate the function, depending on the perspective, depending on how you foresee using that function. But of course, that's not the main point to make. But looking into the quality of the code, so maybe we can look at the process as well to adapt the process to generate the function like the first thing. And the other thing is you could, related to the first question, you could also use like DSL, domain specific language, to generate the prompts. The other day I came across in the paper, more or less like that. So, part of the problem might be in the quality of the prompt. So prompt is not precise enough or elaborated way that guides code generation. Sorry, that's not sense.
Are there any more questions? Go ahead.
Yeah, you were using Python code.
So currently we are only generating Python code. We're also considering to ask the LLM to translate from one language to another. Any questions? Any more?
Any remote questions? Anybody wants to ask? I do not see any questions, so.
Thank you.
Thank you very much. And the last talk of our session is remote. Amit, can you try to share your screen?
Yes, sir.
Go ahead. Try again.
One second.
Sure. Okay, I think the screen sharing works. Yes, and you went to the full screen mode and everything looks good.
Is it fine? Can you see the full screen?
I can see your first screen and I can hear you very well. If in the room and any problems or anybody else, please raise up. But I think we are ready for your presentation. Go ahead.
Thank you very much. I'm Amit. Today I'm going to talk about our work, illuminating the hidden challenges of serverless LLM systems. So in recent years, the LLM has been adopted in different domains such as education, sports, healthcare, etc. And these LLMs has comprised of hundreds of billions of parameters, and they have remarkable capabilities in terms of the reasoning and text generation. However, they require massive computational resources such as GPUs, TPUs, etc. The problem is that when you deploy this kind of large language model, they incurs high cost and you have a lot of operational complexity, and also the resource you have see a lot of resources which are underutilized. Generally, you deploy this kind of LLMs through dedicated GPU cluster or some persistent infrastructure. However, they incur high fixed costs. Whereas, if you consider the serverless platforms, they're mostly provide elastic scalability. Therefore, it can auto scale based on the demand of the particular application, and also you are provided the fine get billing. Basically, you pay as you much you use basically, and also the operational simplicity is very low because you do not need to manage any kind of infrastructure. And also it provides event-driven execution where it can execute on demand based on the user's prompts or the application requirements. And currently, this kind of serverless can be accessed to different kind of web APIs, and some of the platform does provide data processing and IO back and as well. Uh, However, the serverless are not really designed for GPU intensive and stateful workload. So therefore, there is a lot of challenges that you need to um, overcome in order to provide a serverless LLM framework. So in recent years, some of the LLM serverless works has been done by few of the researchers, and they provide enable developers to seamlessly integrate state-of-the-art LLM capabilities without infrastructure management burden, and it allows you to pay for actual users, and while it can benefit from the auto scaling as well. So the benefit of the serverless LLM framework is that it can provide democratization, where it making cutting edge AI widely accessible for all the users, and already it can provide cost efficiency because it can eliminate ideal resource costs that you can generally incur normal LLM framework. And the operational simplicity is basically low as it abstract over the infrastructure complexity, and the electric scalability does provide better handling of the unpredictable workloads automatically. However, there is a fundamental challenge is because they have a dichotomy between the serverless function and an NLM inference basically. For the serverless function is mostly generally used for stateless and ephemeral functions, whereas serverless LLM inference is basically stateful and persistent. For the serverless functions, mostly the serverless functions are really small, mostly in MBs. But for LLM inference, they require massive memories. It's from 10 to 100 GBs. For serverless, the another most important challenge is like cold start time initialization. For LLM inference, if you're not using if you're using dedicated infrastructure, then you might not require any kind of cold start. For serverless function is provide a fine-grained resource allocation at the function level, but for LLM inference, you have code scale, GPU requirements, and resource allocation. Another important fact is that for serverless, it requires stateless execution, but for LLM inference, it requires stateful execution, and it requires conversation histories and KV caches to be managed properly in order to provide better performance. So therefore, this mismatch creates several unique technological challenges that must be resolved. So in the current landscape, there are four categories that we have considered. The first one is like traditional model serving framework, which are TensorFlow serving and Torch serve. The limitation is that they're mostly persistent deployment and no scale to zero. For then we consider the general serverless platform, which is basically AWS Lambda, Azure Function, or IBM Function. They do not have native GPU support, and mostly they have a severe cold startup time. A third is like serverless LLM optimizers such as VLLM and TGIs. These are persistent clustered, and they do not have a no pay per use model basically. So you have to pay like for the entire duration that you are kind of using the cluster or deploying the LLMs. The fourth one is like emerging LLM APIs, which are OpenAI, Anthropic, but they have a black box and the limited control that can user can exploit basically. So this is the one of the table that in order to we kind of used for the gap analysis of the current frameworks. And from our key finding is that no single category supports all the requirements in terms of the interface temperability, and then multimodal approach, then cost control, dynamic selection, cost task sharing, then cold start minimization, and GP provisioning. So and also as I was talking about, the one of the critical gaps are like you need to manage the cold start mitigation, and also you need stateful execution and fine-grained GPU provisioning. There are partial support for dynamic selection and cost sharing. However, in order to manage all the requirements, you need some kind of new architectural approach. So therefore, we propose an architecture where it has three main layers. The first layer is user interface. So it is a declarative interface layer, which is important for in order to provide intent-oriented APIs to users. And the second is like adaptive orchestration engine, which is responsible for dynamic pipeline synthesis and also cost task optimization. And the last one is the serverless runtime in order to support a state mitigation, like cold start mitigation, and also state management for the LLM KVs and also GPU provisioning. So we'll discuss each of the layers in detail. So the first one is declarative interface. What do you mean by that? So it is an intent-oriented user experience where it should abstract away the model architecture and the resource requirement, and users should be able to specify the desired outcome, not the implemented details, because we are considering here like serverless, and we do not want any kind of like infrastructure related implementation. And the key features, it should be like it should allow us to provide natural language queries, and it can provide some temporal specification like based on the application requirements, such as synchronous, asynchronous, and stateful session based on the what kind of application you are executing. And also it should apply a multimodal support, so it should generate text, image, audio processing as a unified workflows. And also we feel that like users should be able to provide some kind of cost and SLO control, such as it can provide that this is the budget limit per invocation of a particular function, or how much latency and accuracy should it target in order to provide better SLOs to these different kind of like users applications. The second is adaptive orchestration layer. So it is basically responsible for intelligent pipeline synthesis, which is basically it transforms the user intent that we submitted in the previous layer to an optimized execution plan. So it follows a process where it first analyze the task based on the queries that users given, and then it selects that particular LLM, optimal LLM, which is basically provide better inference results based on the SLOs that a particular application is targeting. Third one is like pipeline composition. It might, if you requires multiple models to be chained together, then you can use that particular third pipeline composition step, and then it goes to the optimization step where it helps to apply sharing different kind of resources, and it can do batch optimization. And the fifth one is deployment planning. So once the optimization plan is done by batching, and then it can map to the available resources for the actual execution. And also it has some kind of adaptive capabilities where it should be able to monitor the performance metric and dynamically reconfigure all the resources based on the load. And also it should be able to perform different model switching for cost and performance data. So this is the overall architecture of the orchestration engine. The third one is efficient serverless runtime. So it should bridge the execution gap. Basically, the serverless platform are built to use stateless infrastructure, but it should be able to able to have a accommodate for stateful pipeline execution. And also runtime components should have a resource manager, which should dynamically provide the GPU provisioning and memory management across different tenants. And also it should have a cold start mitigator, which can predictably preempt some of the components of a particular application, and also should be able to snapshot for the GPUs in order to better mitigate the cold startup time. And also that should be like a state manager, which can allow basically efficient distributed of the KV caches for LLM inference. And also should be able to persistently store the sessions for any of the users requirement. And also the SLO enforcer basically is responsible for real-time monitoring and dynamic trade-off decision for different kind of SLO requirement from the users or the tenants. However, in order to realize this, all three layers, you have to overcome different challenges. The first challenge is the cold start latency, which is a really old problem for serverless domain, but you have to re-imagine for the LLM serverless framework. Traditionally, when you have the serverless platform, when you have LLM serving platforms, they do not really require cold startup time if you are deploying them in a dedicated infrastructure. But for serverless LLMs, it might incur a huge amount of latency because you have to load really large model basically. So what are the mitigation strategy you can employ in order to lower the cold startup time? The first one is predictable preloading. Basically, what it does is analyze the user patterns and keep one instance during peaks. And the second one is like GPU memory snapshotting, which can basically save the fully initialized model state and rapid restoration from the snapshot in order to mitigate the cold startup time for the different LLM models. And the third one is progressive loading. So basically, it can just load critical layer first and then stream remaining parameters based on the requirements. And also we can also exploit different kind of specialized hardware, like for persistent memory, you can use Intel Optane DC in order to store the different intermediate state. And also we could use rapid context switching GPUs, but those have different performance implications. So you have to have balanced approach in order to understand the complexities of such context switching. Second one is challenges like resource sharing and isolation. So right now, in order to provide better performance and efficiency data for multi-tenant users, you need to share the expensive GPUs across users, and you need to maintain some strong performance isolations in order to provide better performance. And the solution strategy in such case should be lightweight GPU multiplexing, where you time slice the transformer error scheduling, and also memory partitioning with QS guarantees. Also, we could have like intelligent batching, basically group compatible requests for different users, and respect individual latency SLOs. And we could also use different kind of isolation mechanism based on the hardwares. The third one is basically the state management. So this is very important for the LLM application, because when you were talking about LLM applications, we have to store different sessions and conversation history. So therefore, it is important to provide better state management, such as for the KB caches, you have to maintain the different attentions for different LLM models. And also you need to have a state management for immediate results, because you have to need to multi-step reasoning. However, the main problem or challenge is like how to make the stateless infrastructure stateful. the fourth challenge is like, can you predict some of the LLM inference workloads performance? So in order to do that, you need to have see the different trade-offs for the different complex factors such as input length variability, then system load fluctuation, and the resource availability based on the different users requirements. So in that case, the solution strategies could be the prediction models where you can have a latency estimation and cost projection, and more importantly for the LLM inference, you could have a accuracy prediction based on the what kind of models you were using, and also you could use continuous learning in order to adapt to new models and pattern and handle cold start for prediction. So based on these challenges, in order you can realize the architecture that we propose. So in conclusion, our contribution is that we kind of identify the challenges for the serverless LLMs, and we propose a comprehensive three-layer solution, and we propose an outline critical problems requiring investigation. So in the future, we would like to implement these different components and benchmark different LLM systems and exploit hardware software code design opportunities. Thank you. With that, yeah, I'm happy to take questions.
Thank you. Do we have questions from audience, local or remote? I have one question. When you describe the high-level goals for the serverless system, does it include like agentic operations? Like what happens when you tell it to run some prompt or description of the function? Does it just run it, or does it divide it into smaller parts and deploy the multiple versions? How does it deal with more complex functions?
So ideally, it should be able to divide small functions and then run it. But for that, you need to know that what kind of application you are running. Like if you are running very complex application which has a lot of IO dependency or data dependency, then you have to carefully would be allowed to do that, but I don't think any of the existing like serverless LLM platform does that. So you need some better understanding of the workflow that you are running, and based on that you should be able to provide those information to the platform that we're designing. That's why we're saying that we are kind of providing intent-oriented infrastructure which should able to provide the user's intent so that it can divide those different models in small parts and then execute them.
Okay. Sounds good. Is that what is the, if any of your thoughts about like, running today, you can run an inference for AI with multiple models and then kind of provide it as a service in the sense serverless. The models are loaded when they are needed and then, unloaded when they are not needed. Is that part of what you describe?
Yeah, that is one of the things. Like you can switch the models like based on the whatever, like some of the models, like if you're designing a serverless LLM inference system, so ideally the system should be able to switch the models based on the requirement. Like suppose some of the models are being requested very frequently, which is very hot, right? So you should keep those things in the GPU's memories for the longer time, as long as like you see that there is a pattern that is the like predictable. That's what I'm saying, that predictability does comes in. Like you need to predict that like these loads are coming for this kind of models, so you should keep it in the GPU memory. If it is not, then kick them out from the GPU, then maybe load some other models which is kind of requested frequently.
Okay. Are there any questions?
I do have a question, please.
Go ahead.
Thank you for the presentation. My question is regarding the energy consumption of these LLMs on serverless. Have you seen anything on that direction in the sense that should it reduce or should it increase the overall consumption of LLMs?
So we haven't looked into the energy consumption aspect, but there is a paper called Dynamo LLM, so it just does that analysis for the energy consumption. But I think this could be done for the serverless application. But the issue is that like mostly we're focusing on the performance instead of the latency and the accuracy right now. So this could be one of the potential aspect to look into the future.
Thank you.